So let's take a look at how power works within hypothesis testing. So if we recall, last week we talked about different types of variables. Two of our main effects variables, right, are looking at our independent and our dependent variable. We have a null hypothesis, which posits that there are no differences between groups, no relationship or associations between variables. Alternatively, we have our alternative hypothesis, also known as our research hypothesis, where we do posit that there is a difference between groups, or that there is a relationship between variables, or a correlation between variables. And within this alternative hypothesis, we have different types of alternative hypotheses, whether it's non-directional, which is your two-tailed test, or a directional hypothesis, which means it is a one-tailed test. And of course, we know we have a correlative alternative hypothesis where we posit that there is a positive or negative correlation, or that there is just some type of correlation. Right? So again, we have directionality, positive or negative correlation, one-tailed, or that there is a correlation, two-tailed correlation. So when we are trying to do a power analysis, there are a few things that we need to know prior to doing the analysis on the calculation using the software. First one is the probability of committing a type 1 error. And if you recall, this is our alpha. What is our typical alpha level that we set whenever we do hypothesis testing? Alpha is usually equal to 0.05. So if we turn that 0.05 into a percentage, that would be what? 5%. And so the way we think about the probability of committing a type 1 error, or what alpha is that this is the error of the first kind. We reject the null when it is actually true. Also think of it as a false positive. If alpha is 0.05, what this means is that we are giving ourselves 5% probability of making an error. The error is that we reject the null when actually it is true. The null hypothesis is true, but we rejected it and we made that incorrect conclusion. Beta, also known as the probability of committing a type 2 error. Right? So type 2 error is the error of the second kind. We failed to reject the null that is false. The null is not true. The alternative hypothesis is true, but we failed to detect that significant difference. We failed to reject the null even though the null hypothesis is false, hence a false negative. And so a lot of the times we tend to keep this at about a 20% probability of making this type of error. And so if we usually give ourselves about a 20% probability of making this error, which is our beta, if we subtract that 20%, which is our beta, from 1, this gives us our power. So typically, we set our power then to be what percentage? 80%. So we would say if our power was 0.8, we would say that it's 80% probability of detecting a significant relationship, or 80% probability of detecting a significant difference when one actually exists. We also have the effect size. We'll talk about that a little bit more, but essentially the effect size is the magnitude of the difference. How big of a difference do you plan to detect? A small difference, a medium, or a large difference? And the last one is directionality, right? One or two-tailed test. Again, this is based upon your research question and ultimately the hypothesis that you posit. Do you posit that there's one group's going to be more or less than another group? Or do you posit that there is going to be a positive or a negative correlation between your two variables? So if you posit that there is directionality, that one group is more or less than another, or that there is a positive or negative correlation, then you are doing a one-tailed test. And a two-tailed test, non-directionality, requires a larger sample size. So hopefully you've seen a similar table like this before, where if you're looking at the rows, this is if we are going to reject the null hypothesis. or we're going to fail to reject the null hypothesis. Whereas the columns, the null hypothesis is true, whereas the null hypothesis is false. So this is the true outcome, whereas the rows are what do we as the research scientists decide to do based upon our analysis and based upon our results. So if the null hypothesis is true and we fail to reject the null hypothesis, then we've had the correct outcome, that there really is no relationship, there really is no difference between groups. We've got the right outcome. Conversely, if the null hypothesis is false, and we in fact reject the null hypothesis, again, we have the correct outcome, which is a true positive, and this is where we have our power, our ability to detect a true difference or a true relationship when one really exists. But looking at type 1 and type 2 errors, type 1 error is if the null hypothesis really is true, however, we actually rejected the null hypothesis. This is a false positive. This is our alpha. We give ourselves 5% probability of making this mistake. However, the type 2 error, our beta, right? The null hypothesis is really false. There really is a significant difference, or there really is significant relationships or correlations between our variables, but we failed to see that in our data. We failed to reject the null hypothesis. We did not reject it. Our p-value was greater than 0.05, hence we made a type 2 error, and we're giving ourselves 20% probability of making this type of error. This is known as our beta. So hopefully the idea of alpha, which you've learned about and applied in statistics before, is now being a little bit more reinforced here when we talk about alpha and beta and power. So what is effect size? So it's the magnitude of an experimental outcome or the strength of a relationship between two variables in a sample. So R, correlation coefficient, is also a type of effect size. If you recall, Cohen's d is also an effect size, eta squared is also an effect size. So different types of statistics can be used as effect sizes, and correlation coefficient is just one example of that. And so thinking about the R, the correlation coefficient, if you have an R that's about 0.1, this would say that you would have a small effect. 0.3 is a medium effect size, and 0.5 is a large effect size. But what this means qualitatively, right? Small effect does not mean trivial, but depends upon the context and nature of a dependent variable. For example, let's say you're looking at sizes of a tumor, right? A millimeter versus a centimeter, and sizes of tumors can be such a huge difference. So the ability to detect such a small effect, right? A millimeter of an inch can mean the difference of, I don't know, someone living or dying, right? That small effect does not mean it's trivial, right? But if we're talking about weight loss, a small effect, right? Half of a pound does not mean much in the scheme of weight loss, right? So when you think about the effect size, you need to think about the context in which you are talking about your outcome, your dependent variable. So to give us some idea of how this comes to play and how it relates to your sample size, if we want to determine power, what we have 0.8, 0.6, which are our rows, and then thinking about our effect size, we have a columns of 0.1, which is a small effect, 0.3, which is a medium effect, and 0.5, which is a large effect. These numbers here, 491, 55, 20, 784, 86, 30, this is our sample size. So think about this. If we wanted to be able to detect such a small effect, that such a minute difference between groups would be significant, And our ability to find that in terms of our power, 0.6, look at our sample size of about almost 500 people. But if we wanted to have stronger likelihood, right, more power, the likelihood, lower likelihood of committing a type 2 error, we need to then increase our sample size to 784. But think about that, right? Think about the feasibility of recruiting that large of a sample size. So if you recall, the beginning of part 2 of this lecture, we said that the minimum sample size that you should have should be what? 30. So we see here, right, and our power at 0.8 and our large effect size at 0.5 gives us a sample size of 30. Detecting a smaller effect size or more nuanced relationship requires a larger sample size, right? That half of a pound, we may not see that difference. It may not be statistically significant in our sample of 30. But in our sample of 784, that half of a pound difference might show up to be statistically significant. So here are 3 additional resources that I highly encourage you to read up on. You don't necessarily have to do these, but I encourage you to read up on these because these are going to be more of an application of power analysis. This first one is the actual software in itself. You're more than happy to download it, or you're more than welcome to download this if you wanted to use it, but you don't have to do it for your project. Second one, role of effect size in power analysis. I encourage you to read this. And then power analysis for 2-group independent samples t-tests. This gives you 2 different scenarios in which you would utilize power analysis when you're looking at differences between 2 different groups given 2 different scenarios. I will say, for your project, every single member in your group is required to survey or to collect data on at least 25 people. So if you have a group of 5 people, every person in your group should at a minimum collect data on 25. Your minimum sample size for a group of 5 would be 125 students. So for your group, the minimum sample size you need to have for your project at the end of the semester is 25 students per person in your group. Okay? All right, so coming up next week in class, we will talk about instrumentation, we'll talk about measurement, talk about levels of measurement. So if you recall, we have 4 levels of measurement: nominal, ordinal, interval, ratio, and then we'll talk about psychometrics, talking about the ideas of reliability and validity. Now that homework 2 is done, I'll have those graded for you and ready to return next week. But in the meantime, you should be working on your draft of your proposal, because in 2 weeks after our lecture, we're going to have a peer review in class where every group is going to switch and provide another group a copy of your proposal. Sit down, you're going to read up on it, and provide some feedback. So I encourage you to start working on your proposal if you haven't already, and to take a look at the peer review directions and what the peer review is going to look like in terms of what you're going to be turning in to me and you're turning into another group. Okay? Have a great week. I'll see you guys next week.